All right, so California Soul, that was the song we play. And one of the reasons I love about California is because I like outdoor activities. So one good thing about California is that typically this is the weather you would imagine in California, but apparently not this weekend. So the past weekend, right? And so but like when today I was interviewing someone who is interested about a job position here, and he was asking me like, well, what are the good thing about UCR? And I talked to him like, okay, because it's in California. Anyway, um, all right. So today we are going to continue our discussions on hardware accelerators, but today we are going to shift the angle a little bit from domain-specific accelerators to general-purpose computing. So, like the landscape of modern computers are pretty much like this, right? So, as we mentioned before, nowadays in our computers, we not only have the CPU, but also GPUs and many AI accelerators, and some of the new commercials would try to advertise their product as something like XPU, accelerated processing unit, but this X could be some kind of applications, and sometimes you put an X, it sounds unknown, it sounds more powerful, well, mysterious, right? Like I don't know how many of you watched the X Files before. Did you? No? Okay. Then I was probably too old for that. But sometimes, right, like people like that kind of advertisement. But no matter what kind of PU it is, right, like it's TPU, XPU, or whatever, it's some kind of hardware accelerators that are domain specific. And in the last week, we also talked about a little bit about FPGA. So a lot of people are fascinated about the idea of FPGA in a way that, well, you can implement application specific hardware, but still make it reconfigurable. FPGA is good for its flexibility. And another thing which Microsoft tried to advertise or say like claim why they like the idea of FPGA is because you can basically reuse the same FPGA for years. However, there's nothing like good in all aspects. And one drawback that I can see from FPGA is the performance limitation, right? So a lot of cases, because FPGAs, they are not designed to be application specific in general, and they are pretty much limited by the speed of SRAM. And if you're familiar with about the RAM cell design, making SRAM faster is still a big issue. And needless to say, other RAM technologies. So, and the other thing is that if you think about the SRAM, it's very expensive. So you are not going to put a lot of SRAM cells on the same hardware. So otherwise, it could be really expensive. So that's why you see a data center class FPGA. They typically would sell you for more than 2,000, and like the ones that Microsoft are using, I think they are more than 1,600. So they are not cheap, right? Although compared against the current generation of data center GPUs, they are still cheaper. But in the meantime, if you compare the performance, for some important workloads that we are looking into, they can deliver good enough performance, but they are not outperforming CPUs, for example. So that's where FPGAs are. So a lot of people would consider FPGA as one type of accelerators. I would be more conservative on that because sometimes they are faster if you do it right. However, if you want to do it right on FPGA, that's very, very difficult. So I've been talking a lot with a lot of researchers on FPGAs, and I do have a student in my group working on FPGA. And we had a hard time making the FPGA outperforming CPU in most of the cases, even with the workloads that advertised by Xilinx. So I personally are not sold by the idea of FPGA after my real experience. But since Microsoft has some real experiments on that, and the other thing is that they probably have more mature engineers than our grad students, so that's probably why they can make the economy work. So on the other hand, right, if you are really interested about like the idea of FPGA, make sure that you are the expert who know how to optimize the FPGA performance, and I'm sure you can find a job in Microsoft. All right, so that's where we are. However, if you look, as I said, right, each of the hardware unit has their pros and cons. So for example, like this accelerators, they have high performance, but they are very specialized. And for GPUs, they are general purpose for regular workloads. However, if today your workloads are not regular, there's not too much you can do with it. And for FPGA, they can offload CPU. So your CPU will feel lighter. However, are they really better? The answer is probably not. So now my thought is that the big question, the big research question for the topic that we are going to talk about today, we are all thinking about, can we find a way to take advantage of the high performance from hardware accelerators, but also make the hardware more programmable? So that's where we are today. And today we are going to talk about quite a few different papers talking about this. So last week we talked about neural acceleration on general purpose approximate programs, and I think I have a mental homework for you, and I don't know how many of you went through that question during the weekends. Probably not, right? Enjoy the rare rainstorm in California, I guess. And then I'm going to talk a little bit about edge tensor processing units, which is the accelerator that are provided for this class, as well as some of my research projects rely on that. And then we talk about TCUDB research project that one of my student did, and also RTNN, another interesting paper that tried to use ray tracing cores for accelerating nearest neighbor search. So those are the topics that we are going to cover today. And let's continue the discussion on this neural acceleration for general purpose approximate programs. And if you remember, this is the process of the concept of approximate computing on NPUs. And so can some of you summarize the whole idea behind approximate computing using NPU? Like maybe in 1 or 2 sentences. What's the okay, Cameron?
Less accuracy for more like power energy efficiency.
Okay, so it's less. Okay, so how about the system level idea? So what you're talking about is a benefit, right? But how about the idea that make the benefit happen? Okay, we use neural network models to approximate a computation, right? So, so what kind of hardware can actually apply? So in this paper, they assume something called neural processing unit, right? And in fact, neural processing unit is a term that's right now used a lot in our like commercially. So for example, if you check the design of Apple's latest mobile phone chips or even the desktop chips, they would have a neural engine, right? And people categorize that as a neural processing unit. And Intel, their GNA, that's also considered as some kind of a neural processing unit. And Google Tensor has been considered as some kind of neural processing units. So it seems like people are using the term AI ML accelerators together with neural processing units. So if you consider neural processing unit as an existing AI ML accelerator, then this idea can actually be used in a lot of platforms right now. So today I'm going to show you a demo how we can apply this idea. But before I do that, I do want to introduce, yeah, they call neural engine, right? So I do want to introduce the idea of the hardware called Edge TPU, which is something that's provided in our cluster for this class. But before we talk about that, right, what is Edge TPU? So we talk about the paper TPUs, right? And in fact, at Google, they have several different variations of TPUs. So the first version is TPU v1, which is a 2017 paper that we have read. And last year, they have the TPU v4 paper. So you know that publicly, they have 4 different generations of TPU, but everybody knows that there is a 5th generation that's currently in production, and that's internally available at Google. So that's the variants of Google TPU. And this line, they are called cloud TPU. So if you are at Google, or well, they typically call this data center TPUs or cloud TPUs. And the rest of them, they are falling into the category of edge TPUs. So the reason why they named them edge is probably because of the turn of edge computing, right? And edge computing, I personally feel this is a very interesting term because it's typically, people typically refer the term of edge computing as mobile computing. So what does that mean is that in modern world, people consider edge computing as some sort of mobile computing in a way that we are able to perform computation on embedded system, embedded device, or mobile devices that are closer to the user. So that's the name of edge. And because it's not in a data center, so people will consider it's on the edge. So that's why it's called edge computing, a very silly term. But what does that mean is that this kind of TPU, they are designed for small devices like a mobile phone or even like an IoT device. For example, like a Google Home, right? What was the name of it? Is it like Google Home or Google Home? Yeah, yeah, because I'm not super familiar with the Google product, even though I got money from Google when I work as an employee there, right? But well, don't talk about that too much. Okay, so here are all the variants. So this is a very good table. I personally feel proud of this table because I don't think anyone ever done it. So this is like a table that listed all the publicly announced version of TPUs. So on the data center side, we have 4 generations of TPU. So the first one is actually in production in 2016, and the 4th version is 2021. And people believe TPU v5 is already in production last year. So, but there's nothing told about it, so we cannot put a number here, and they didn't announce any number there. And the first generation of TPU, as you learned in the paper, they only support integer A computing. So that's 8-bit, right? And it's only accessible in Google Cloud. And if you want to program on it, the only way you can do it is through the TensorFlow and PyTorch. And it's not the PyTorch and TensorFlow that you can access publicly. It's the spatialized version in Google Cloud. So sometimes you might need to adjust your code differently in a Google Cloud because of that sake. And the tera ops per second they can achieve is actually 95. The power is 75 watts. So another thing which I think Google is trying to advertise you is that although we do not have the best performance, but we have the best energy efficiency, and especially compare against the GPU. So you see, like the first version of the GPU, if you are able to pay 1 watt of power, you are able to get 1.27 tera ops. And the device memory is 24 megabytes. And if you look at the 2nd generation of the TPU, and if you directly look at the TOPS, you feel like it's a downgrade, right? It was going from 95 to 45. But be careful about that. The precision it supports actually goes up from 8 bits to 16 bits. And because of this additional bits, it's more area consuming. It would take more power. So as you can see here, the area efficiency is significantly worse, but still better than the GPU at that time. And another thing is that I don't know if I ever mentioned this, but in matrix-based problem, right? Matrix is embarrassingly parallel. The computation of matrix problems are embarrassingly parallel, which means that you can use the tile algorithm to unlimited to parallelize the program almost like in an unlimited way. So instead of building a giant GPU, TPU that give you a lot of TOPS, the strategy of Google actually changed. They try to put like 4 different TPUs as a single pod. So turns out that in each machine, they equipped with 4 TPUs. And if you get this like 45 times 4, they are claiming like each server, each GPU pod would actually give you 180 TOPS. So, but another reason which I believe why they don't actually build a giant TPU is because if you look at the power consumption, it's 280. That's already a lot, right? So another thing that Google mentioned is that you want to control the power consumption and make sure that everything is air coolable. So that's why they didn't take the strategy that NVIDIA used to build a giant chip with a lot of effort in heat dissipation. And the device memory has significantly increased to 64 gigabyte. And there is a reason for that, because for the first version of the for the TPU, they are integer data and they only store quantized data. So and the matrix size they are dealing with is only 256 by 256. So 24 is good enough. However, here we are dealing with BF16, and the accumulation is actually in 32-bit. So you actually want a lot larger memory space for that. And the other thing, so that's why the TPU V2, you see a significant growth in memory space, and as well as and the other thing is that if you want to support these flops, you also need to make sure that your data supply is smooth enough. And if you only provide like just good enough amount of data, it's not going to oversubscribe the hardware. So what you can only do is that you have to be more aggressive, and you need to have like maybe double buffering, a lot of this kind of mechanism available, so that you always have data that's already ready in the memory, right? And as you in a very fast memory, and as you learned in the roofline model, if everything is most of the time in the fastest memory, you are less memory constrained, right? So that's why they make this giant device memory in the second generation of the TPU. And now for the third generation of the TPU, it's pretty much close to, it's a revamped version of the TPU V2. So that's why they don't have a paper of it. But I think in a lot of spec, we can pretty much think it's an improved version of the TPU V2. And TPU V4, that's a paper that you have read. And as you can see, the TOPS per watt is actually even better than the first generation of the TPU. It reaches like 1.62, and the TOPS is 275 for each. And the power consumption is lower. And but one of the reasons why the power consumption is lower is because they also use a better process technology than the version before. However, not too much detail has been told about what their internal architecture looks like. So I don't know what kind of magic they actually have in their microarchitecture. But that's the 4 generations of TPUs that we have right now. And also now, what is Edge TPU? So Edge TPU is the smallest version of the TPU. And it's first announced in 2018. And this one also has a precision at int A. So at some point, if you compare the spec, right, and it's also like 8 megabyte of device memory, and the matrix multiplication hardware supported by Edge CPU is actually 128 by 128 by 8 bit. So at some point, I was thinking this is more like a trimmed down version of the TPU V1 because you can consider this edge TPU, its core is actually quarter of the size of the matrix that it can deal with. And the other thing is that because the matrix size is only a quarter, right? So it's not too surprised that the device memory is also shrink in proportionally, right? So that's why I initially considered the HTPU as a shrink down version of the TPU V1. And unlike its siblings in the cloud, HTPU is the only one that you can purchase from Amazon. So actually, I think I bought a few one and I built this board. So as you can see in this board, okay, so this board is a PCIe board that I built, and in a cluster that I give you guys, one of the machine is actually equipped with a few boards of this. So you can actually access it from the Data Hub service that we provided for this class. And this guy here is actually an HTPU. And on this board, I actually put 4 different HTPUs. So you can consider this is a and there is a heatsink. So this heatsink here, there is a chip is like a PCIe root complex on this board. So actually, if you want, this 4 they can talk to each other directly. However, because of the restriction of the architecture, so there's no way I can let them talk to each other. Otherwise, it would be amazing. However, you can pass this along so that you can see like how you can feel how big is an HTPU. And each of this is actually worth like $30 if you are able to buy them. So initially, before the shortage of silicon, it's easy to buy them. But after the pandemic, it takes me for about like a year to get each of this. And initially, I have like about like 20 in my lab, and I purchased another 32. But that 32 actually take me about another year to get them. So, and at some point, I was thinking about I'm not going to get them. But one day, I figured out that there's a amount in my credit card being charged, so I know they're coming. All right. So and this one is publicly available. Oh yeah, and the programming framework here, they actually provide quite a few. So you can actually use TensorFlow or the embedded version of TensorFlow called TF Lite. And the most fascinating part is that it does have a C++ interface that you can use C++ to perform inference and directly control the low-level operations that you want the HTPU to do. So which is a very fancy, which for me, right, this is a very good like platform to do research. So that's why I bought a lot of it. But in terms of performance, 4 tera ops, but if it's only 2 watt, it means that it's 2 tera ops per watt. So it's the most energy efficient version of the TPU. So that's another selling point of HTPU. It's more energy efficient. And in terms of the embedded system, you can actually, the energy efficiency is very, very important. And another way that I use HGPU, right? So it's actually, you can put it in any kind of embedded system. So Google Tensor is a chip that they produced in 2021. And if you have a Pixel 6, that's where you can find it. And however, there are not that many, you can say it's publicly available in some sense. As long as you buy a Google Pixel phone, you would have it. However, it's also not so publicly in a way that you cannot freely program it. The only thing that you can use to program it is through an API and TF Lite. And 27 tera ops with 5 watts of power consumption. So it's actually the most energy efficient version of the HTPU. However, it's private to Google Pixel, and as long as you can root it, you can have more access to it. But from legal ways, it's not publicly available. But it also means that the idea of HGPU can be well integrated into a real system. So here is an example of a real system integration. So this is also one of the platforms that I will provide for the project. So this is a Jetson Nano. And For the Jetson Nano, it's a device by NVIDIA. And this NVIDIA device, well, since it's NVIDIA, so it's not too hard to imagine that you would have a GPU on it. And where's the GPU? So it's actually in this separate expansion board. And this expansion core, this separate expansion board has a heat sink. And this sink, under this heat sink, they have a chip. That chip contains both CPUs and GPU. And what level of CPUs and GPUs it provides is actually pretty close to the ones that are used in Nintendo Switch. So that's one fun fact, right? And okay, so this is the CPU and GPU complex. And under this, there is a circuit board here. And so you can consider this as a motherboard. So it does have like some interconnects. And one thing that I do is that I also put an M2 version of the HTPU on it. And this HTPU doesn't have a heatsink. So you can see like how tiny each HTPU is here. So you are also welcome to pass this along. And if in the meantime, once you touch it, you might have some idea about like what you want to do on using this board, I guess. All right, so these are two different, these are all the variants about TPUs that we have. And the HTPU expansion card, I think I have shown you, right? So each GPU can offer 4 trillion ops with 2 watts of power and cost 29. Although this morning, some people were asking me like how much, how easy can I get one? So I checked the USB version. They are advertised, well, their MSRP, right, is actually like $60, but right now Amazon sell it for 100. I guess it's probably because of the shortage. And if you want to buy it from MSRP, the lead time from Mouser Electronics is actually like 7 weeks. So that's a very so it's not likely to get it before the end of the quarter. So if you are thinking about like using the USB version of the HTPU for your project, you probably have to wait or pay more, right? Time is money. So so each of the expansion card that I have, it would actually contain 4 TPUs, so you get like 16 tera ops per card, which considered the price is actually not a bad deal, right? Okay, so in our cluster machines, one thing that we do is that in addition to GPU, we can put HTPUs alongside with it. So now, given that you have that kind of machine, right, and consider that you have learned the idea of approximate computing on NPUs, and now I'm giving you a sample, a toy example, toy program. So this program is like this. So I am doing matrix multiplication, but this matrix multiplication, let's make it simple. It's 4x4 matrix and 4x4 by 4x2, right? So the result would be 4x2 as well, right? But let's make it even simpler, right? So because the thought that I have here is that I want to do something like a BNN, right? Like a binary neural network. So suppose every result should be just 0 and 1. So after I get the result, I also do a thresholding. And the thresholding is pretty much like, okay, if the value is more than 2, is equal or more than 2, then the value should be considered as 1. Otherwise, it should be 0, right? So it's so if you get a result like this, then the final result that I should get is pretty much like this. Sounds good? Okay, question?
Yeah,
Why is 1 converted to 0? Because it's lower than 2, right? Because you have 4 elements, right? So the maximum value you can get from each cell is actually 3, right? So if you take a threshold in the middle, right, it's either 0, 1, 2, 3, right? So it makes sense that if it's lower than 2, you make it 0. Got it? Okay, so this is the problem, right? So if you are given this kind of problem, talk to people around you. How can you apply the idea of approximate computing on NPU to solve this problem?
you bring that to 0 and 1, you would say what's I mean, the NPU, like in the paper, they use machine learning. So I don't know. It's like you like self. I don't know. I can't put it into words. It's like a self-reference kind of thing, I guess. Yeah, true. Is that real? I don't know. I don't know. Yeah. They do approximate the results, but like at that point they already computed the actual results.
All right, so you know how to make it from a paper to real implementation. So today, if I said that the only thing I want to do, or say for this particular program, this 4x4x2 matrix multiplication is what most important to me, how are you going to do this? How are you going to apply the concept? Any thought? Any thought?
I guess we would train it on a whole bunch of data.
Okay. How, when you say whole bunch of data, what are the data?
Like a whole bunch of matrix multiplications, right?
Mm-hmm.
Get the answer.
Look at all of it. How do you get the answer?
I guess we'd have to get that data set from somewhere. Maybe some.
Do you have to get it from somewhere?
You can compute it yourself.
You can compute it yourself, right? The algorithm is already known, right? Yeah. Okay, so you get a data set and you generate a ground truth using the real algorithm.
Yeah.
What's the next step?
And then we have to make an AI ML model.
You can make an AI ML model, okay? And so basically, when you say make, you are referring to training.
Yes.
Okay, and what's after?
It trains on it, and then that's all the data. And then you start giving it test inputs to see if it actually works.
To see if it actually works. And what if I am satisfied with the result?
Then I guess you would put it into implementation.
You will put it in implementation, but how do you put it in implementation? Replace the function with the model, right? So you guys pretty much get it, right? So here's the thing, right? How to make the idea of NPU, right? So first of all, think about if I can reformat the input of output as a machine learning problem, right? And then you can start to generate the training and validation data set by running this algorithm in real, right? And you probably cannot run too many data sets, right? Given an algorithm like for matrix multiplication, think about how many inputs are possible. So like for this particular problem, right? I already kind of like limited the amount of input to just 0 and 1s. And one of the matrices has like 8 elements. The other one has like, one of them has 8 elements. The other has what was that? 16 of them, right? But even with this, you already would get 2 to the 24 different combinations of the inputs, right? And creating this many inputs and generating their result would be really time consuming, right? So you're not going to do that. And so most of the time you are going to like randomly create some of the data sets and also as the test input and some of them as the training input, right? And then you will get a model. And if you are satisfied with the model, then you can train a model, you can run an algorithm, replace the algorithm as inference the model, right? That's pretty much the idea. So the demo today, what I'm going to show you is that, like as I said, right, our cluster has the edge CPU, and how can I apply the idea of how come is not working? Okay, so give me a second. I guess there. I hate the network here.